this session. We are 2 minutes already into the session. I want to introduce our first speaker, Nikolaus Frohner, who is with the Technical University of Vienna and who is a PhD student, if I read it correctly, at Professor Bögl. Please start with your presentation.
Yeah, hello and welcome everyone. Thanks for this nice introduction. My name is Nikolaus Frohner. My talk is about route duration prediction in a stochastic and dynamic vehicle routing problem with short delivery deadlines. This is a joint work with Matthias Horn and Günther Reidl, and we are from the Institute of Logic and Computation at the TU Wien. Okay, so let's first have a look at the underlying problem. We are given, as said, a stochastic and dynamic vehicle routing problem. So orders arrive dynamically at an online store and they need to be delivered by a set of drivers. And the delivery deadlines are very short, and so within hours. Additionally, we are given stochastic information, more concretely the number of orders over the day, some estimations about the traffic congestion, and also some information about the weights, their bulkiness, which is an influence on the stop times, as we will see. And our task in this problem is to create delivery routes for the drivers, and so a sequence of orders for each driver in which the customers need to be visited and the orders need to be delivered, and we have to decide when these routes should be started. Might not be a good idea to start, for example, with just one order, but to have an intelligent weighting strategy. And our optimization goal is to minimize tardiness. So that's the first objective. And then the secondary objective is to minimize the real costs, the route durations, and also the labor times of the drivers. So we will look at a related problem. For this, we define the mean order delivery time. So given some day and an hour, this mean order delivery time phi is the time needed by an average driver to deliver one order, some kind of performance figure. And the aim of this work is to find a good predictor phi tilde for this mean delivery time. Yeah, and this estimator or predictor can then be used in other problems, as we will see in the next talk, for shift planning. How many drivers do we need at which time? And also, not part of this talk, it may be used for route starting strategies to estimate how good, how efficient a planned order actually is. Okay. And what we do is we make an assumption that the drivers are quite busy all the time and the waiting times in the depot are small. And so therefore we equate this mean order delivery time with the mean route duration, delta R per customer. So we say we have this phi is the expected route duration per customer. So this duration divided by LR, the number of orders in a route at some point in time, or at an hour actually. Yeah, we bin this into hours, and we know that these routes decompose into three components. So the obvious one are the actual travel times when the driver travels around in the vehicle from the depot to the customers or between the customers. Then at the customer, there is some stop time to deliver the order actually to the customer site. And in the beginning of the route, there is the loading time of the orders into the vehicle. And what we do is we tackle the problem with a supervised learning approach. So this is a real-world application, And we collected over a couple of months historical route data. And then we use now this historical data to build averages in each hour on each day. So this is here the average of this mean route durations per customer. And the idea is now to find, use this as an estimation for this phi t. And to take this as a ground truth, to have labels for a supervised learning problem, yeah? So we have this means, say some amount of time needed to in the mean for the drivers to perform this delivery, but also this is a sampling approach. We have also a sample standard error involved, depending of in this hour. The less uncertain this label should be considered as. Okay. Now we have to discuss the features involved to predict, to make the predictions. The main idea is to replace this day and time dependency, as discussed before, with 3 features, namely the load, so how many orders are due in a given hour, the traffic, and the weight of these orders, as discussed before. So the traffic is a factor by which the travel times increase when we compare to some free-flowing traffic based time without any congestion. Yeah, and what is an implicit assumption here is that we have a stationary spatial distribution of the orders over the day, which might not be true, but still we use it as an assumption here. So looking at related work, we look in the literature to find some models discussed and tested so far on route duration prediction for the TSP and also a capacitated vehicle routing problem. So there's this model by Taganzo that is quite intuitive. So we are given a capacitated vehicle routing problem with n orders, and we can decompose the total tour lengths over all tours by decomposing this into some round trip time. So going from the depot to some area where there are many customers. This twice this time here, this R bar, average time to some region. And then the second part is then the relations, the inter-customer times going from one context. And this is a well-known result from Beardwood and others, that this length increases only with the square root of the number of customers involved, and also some depending on the geometry. So A is an area here, and some factor. So this is yeah, this is the model from which we start, and we then customize this model to our needs. So as discussed before, we do not have a capacitated vehicle routing problem, but a problem with time windows, with delivery deadlines. But these deadlines also imply some capacity constraints. And here another simplification is that we have, and that we assume constant average number of customers, per route over time. And then we set up in the first step a Whitebox model where we make use of the 3 features as discussed before: the weight, the traffic, and this intra-customer dependency. Yeah? And we have here combined this over 2 hours to have some smoothing out over the hours. Yeah. for example, to discuss this term. This is from before, this delta n, square root of n length, then divided by n, because we consider this as average of all customers, leading to this term. And also the traffic, we assumed that it has a multiplicative impact on this. So the higher this traffic factor, the longer the time needed to serve one customer. Just give you a basic idea here. Good. So the main goal is also to compare a white box with a black box model. For this, we set up an abstract function here that takes these three features for the current hour t and the subsequent hour, and we implement this as a neural network with 2 hidden layers and 64 neurons and reduced activation function. And the loss function, we use standard least squares loss function, but also weighted, as can be seen here, by the standard errors, so that there is put more weight on samples in which we have more trust. Good. So how is the training done? First, we do some data preparation where we also remove outliers with unrealistic driving times from our samples, and regarding the routes here, and then we average over the hours and days, and for each hour and day, then so we yield in total roughly 1,000 to a little bit more samples. Yeah, and for the white box model, weighted linear regression in scikit-learn, and for neural network training, TensorFlow with Adam Optimizer. So as figures of merit, we compare, since we use weighting here of the label, standardized residuals, and we do 5-fold cross validations, 10 of them, and build then averages. And what we see here are the white box model here and the black box model here, and also do a feature ablation. So here we see taking only orders, taking orders and traffic, and orders and traffic and weight. And by looking at the R squares, we see that this has some quite obvious benefits of combining both features. And the weight is maybe not so important anymore, but still improves the R squares here. Also, we observe some slight bias. So this is the median of the residuals towards an optimistic prediction. Yeah, so the minus here means we have an optimistic prediction. Okay. Yeah, also a sanity check. We look at the QQ plot of the residuals, and to check whether this follows Gaussian distribution, which gives a quite nice fit here. And also here we see that this at this point there's this slight bias involved. Yeah, as further error analysis, we also check, okay, for different order numbers, bins here, what are the separate errors there, by looking at standardized absolute residuals, and we see that the performance roughly looks the same, no matter whether we have a smaller number of orders like here and more orders, where this is always in the range of a median of 1 here. So maybe this is a little bit easier to understand, to grasp, is looking at an example prediction of a specific day. So the blue line is the ground truth, where we, let's say, are at the hour 6 of our planning horizon and had some performance that is like here 10%. One is average performance, delivery time, and then this is like let's say 12% below this average performance. Yeah, and our predictors in the colors, as you can see here, work very similar, so they validate each other to some extent, and also we see that we have quite some variance that is left unexplained. It could also be seen before from the not so nice R square values here. We have here quite an outlier. In this region here, this works better. So, yeah, so the key conclusion is that a substantial amount of variance remains unexplained, and the challenges here are that we have many overlapping noise sources in the data. So the data was manually collected by the drivers. This adds a measurement error already, and also each driver has a different pace, and this also adds driver bias. And yeah, there are many further noise sources that I won't discuss here in detail right now. Or maybe also important, this estimation of the features of the traffic and the number of orders expected is also difficult problems in their own right, and also give also rise to noise. Good. Let's come to the conclusions. So yeah, we created a predictor for the mean order delivery times in this given real-world vehicle routing problem, where we have stochastic information about number of orders, traffic, and weights. And what we considered was a black box model, and we see that they behave quite similarly. We also do not observe much overfitting, probably due to the quite substantial noise. And bottom line is that we achieved the standardized R square of 0.53. And the best result is given by a neural network using all three features here together. And yeah, so possible further work is then concerned with somehow controlling these noise sources or getting rid of them to some extent by not using only real-world data, but also running simulations so that we can have more control over the noise and also refine our models. So that's it from my side. Thanks for your attention. I'm happy to answer any questions.
Thank you very much, Nikolaus Frohner, for this interesting talk. I want to give the audience a chance to raise questions. If there are any, please use the raise your hand feature. If you have a question, Michael Affenzeller has a question, please.
Okay, thanks, Andreas. Apart from the neural network approach you mentioned and reported the results, have you also been considering other machine learning techniques for the predictive modeling?
Yes, we tested lasso regression as well, where we included a number of other features derived from the existing features, like a logarithm, exponential, polynomials. But we did not see any significant contribution there. And also we tried a binning approach where we distributed the traffic more costly into low, medium, and high traffic, and also put the number of orders into bins and train for each situation then a separate model. But in the end, this didn't give so much difference. So that's why, yeah, we stick with those approaches here. My assumption is that or I think that this is the problem lies more in the data and the features, and maybe not so much right now in the model here. But yeah.
Okay, thanks.
Martin has also raised his hand, please.
Yeah, thank you, Mr. Frohner, for your presentation. I was just wondering, as you are using real-world data for the ground truth for your model, you probably can also analyze the stochastic effects that you have in this data. So I was wondering, have you had a look if the effect of traffic jams is higher regarding the noise in your order times in your data, or is the effect of different orders coming in at different locations has more effect on the data? So have you had a look which is more critical regarding your application, the traffic situation or the order situation?
Good question. We didn't make a thorough analysis there regarding the effects apart from this from the feature ablation, where we see that when we use the N alone, we have here the traffic alone maybe, and then this order, this number of orders alone, and we see that the number of orders seems to have more impact on the predictive power. But regarding is this what you mean, or which kind of analysis are you referring to?
You did not any analysis on the input data, so you had a look at the prediction quality of your models, but you have not had a look at the input data to get some.
Of course, we started of course by looking at the input data and plotted some averages where we had the traffic and the number of orders, and the traffic color coded and the number of orders on the y-axis to see, to get an idea of the variation of the variance there, to postulate those models in the first place so that they make sense. We started from there. Also doing some basic correlation coefficients, whether our assumptions are plausible regarding the dependency between traffic and the output and orders and the output, and also between the features, any correlations.
Okay, thank you.
Okay, thank you very much. We have already reached a little bit into the time of the next talk, so I would thank Nikolaus Frohner again once more for his talk, and I would like to move on to the next talk given by Michael Bögl.
Yes, hello.
Who is employed at the Risk Software GmbH in Hagenberg, and he will give us a talk on real-life scheduling with rich constraints and dynamic properties. Please, Michael, go ahead.
Thank you very much. I hope everyone can see my slide. The work which I will present today was done by a lot of people, or done by a lot of people. It is an ongoing project, and it is motivated by practical projects we're doing it at the company. At first, I want to give you a little bit of context, because, as I said, it's a very practical-oriented work. At the company, we do application-oriented research projects and customer-specific software development projects, which means we develop individual software for customers which runs at their site. In the area of logistics, informatics. Relevant domains where we work in is combinatorial optimization, especially scheduling, routing, packing, assignment, and data science methods for regression, classification, and clustering. These are the problem domains we are working in, and we do software for completely different planning levels for enterprises and companies, supply chain planning, then enterprise resource planning, down to the machine operation level. And the next point is important. Customers which turn to us often did not find an appropriate standard solution elsewhere. They are not satisfied with the solution they have, and they expect a tailor-made solution from us, which works as they expect. And in recent years, we find that companies more and more see the need for tools to solve their specific planning problems. And the area I want to focus in this talk is the area of scheduling problems, where companies deal with various constraints and objectives. A lot of constraints of companies are rather similar. For example, they have capacity constraints on machines. There's some type of time constraints, but there are special constraints which are very individual for each company, like types of setup constraints or something similar. And recently we talked to the head of IT at the company, and he said their current automatic planning solution gives good results in about 85% of their planning scenarios. But the time they require to identify and fix the remaining 15%, where the tool does not yield a usable solution, is higher than the complete manual planning process. Which means they have a solution, but they cannot use it. They do the planning manual because the solution is not cannot handle all the cases. And this is the motivation for us, which started the development of an extensible and adaptable scheduling framework, which can be tailored to the customer's needs and which is able to solve real-life scheduling problems with up to tens of thousands of operations. When you solve such large problems and when you deal with complex constraints, the method of choice are often meta-heuristics, which have a generic structure and can be applied to completely different problem domains. And this was done in the company. We realized, even though you can reuse the algorithm, the problem-specific part was always implemented from scratch, which was a lot of work and was very error-prone, and it was very expensive. Therefore, we decided to generalize the problem type and to develop a problem-specific framework for scheduling problems, where we can reuse large parts and can customize certain aspects to the customer's needs. So everything started, and we have currently a data model which is very rich. Scheduling, the problem of scheduling is more or less you have a set of operations which you want to schedule on different machines. And our operations consist of different time spans, setup duration, which can machine independent, production duration, which can machine independent, and some tear down duration. We have setup sequence and machine dependent setup information, transportation times. There are relations, predecessor and successor relations, which can be used to model overlaps between operation. And overlap is something when you have one operation and the next operation, and the next operation can start before the previous operation ends. And for example, you can define the next operation can start when 10 items of the previous iteration are produced. Then we can model the requirement of multiple different machines for an operation. Each operation can have a machine-dependent capacity demand, and of course, we have earliest starting time, latest finish time, and very important, we have the currently planned times or the current state of the operation. This is used for rolling horizon planning, which means typically some plan is executed in reality, and then the reality changes, the environment changes, and you must take the current plan, the changed environment, and restart the planning process. I've already said we have different precedence relation, and we have different machine types. And the machine types are one of the most complex things we have. First, we can, the machine types we implemented can handle unavailabilities in two different ways. The first way is an operation must not be going on during an unavailability, which means they must be finished for an unavailability. And the second possibility, possible handling is that an operation is stretched over an unavailability, which means that the duration increases with the length of the unavailability. This is how to handle unavailabilities. And then we have 4 different machine types. Single capacity machine, where only one activity can be on the machine simultaneously. Then we have the machine type varying capacity fixed duration, where you have the machine can have different capacities at different times, and an operation can only be planned on a machine at times when enough capacity is available. The third type is varying capacity scaled duration. We have again different capacities on the machine, and the duration of the operation depends on the capacity of the machine. And with unlimited capacity machine, where unlimited number of operations can be executed simultaneously on the machine. We see a schedule to calculate the schedule. This is very, very computational intensive. Of course, there are a few objectives. I want to emphasize the last objective, where we have the minimization of the deviation from a given plan, from the planned times. And a short overview of our architecture. Everyone who has worked with meter heuristics know that the algorithm is problem independent, and we designed the problem class also to be independent from a specific from a customer specific problem. The algorithm provides a generic implementation of algorithms with different components, which can be applied to the different problem classes. Then we have the problem class, in this case, the scheduling, and there we have generic implementations for basic data structures. We have implemented logic for typical cases, machine selection strategies, and so on. And then there's a large part with customer specific extensions and logic where we can provide logic which models the customer's problem at hand. For example, the calculation of the setup times, the calculation of the production duration per machine, and we can there provide how we sequence the operations on the machines. This is on the next slide. We used the idea which is from resource-constrained project scheduling, where the solution representation is not a schedule, but the solution representation is an activity list, which is an ordered list of operations, where the precedence relations are satisfied, but operations do not yet have a machine assigned or start and end times. This is customer independent. Then we have a customer dependent logic, the schedule generation scheme. There we can implement the logic of the given customer, how to plan, how to translate an activity list into the schedule where all operations are assigned to machines, all operations have start and end times, and all constraints are satisfied. And this schedule then can be evaluated by the objective. From the methodical point of view, we used a taboo search algorithm from literature. There's nothing special. Just one thing I want to point out. We have one special solution construction method which resembles the old solution, which is then used for rolling horizon planning and to adapt to dynamic changes in the environment. The other methods can be used to construct a solution from scratch. Then we have a lot of neighborhood operators based on publications, and we have a lot of specific operators which are designed for our customer data sets, and they mostly handle tardy operations and setup time and costs. And we have a few random operators to diversify the search. And we have custom neighbor selection strategies. I cannot show you results from customer datasets, but we recently started to model benchmark problems with our approach, and I calculated a few preliminary, I underline this, results. So these results should give an indication on how our solution approach works. We currently only, I have only results for the job shop scheduling problem and the job shop scheduling problem total weighted tardiness. They're aggregated results. There are additional benchmark instances which could be used, but I don't have the results currently available. If we take a look at these instances of the job shop scheduling problem, we see that our approach average between 3% and 20% worse than the best known solution currently, and we reach the optimum sometimes. When we compare the results to the total weighted tardiness instances, we see that we are much worse. So we are not very good yet. We are good enough from a practical point of view, but we want to improve those results because we are on average about 60% above the optimum currently. The last 2 years, we implemented our solution approach, and here I have summarized a few observations I want to present. It seems that benchmark instances are harder to solve with our approach than real-life instances. We don't have a thorough computational study yet available, so we are not completely sure what's the reason, but we are going to analyze this. Another observation is that the real-life instances we deal with are much larger than benchmark instances with much more complex constraints. I must admit that there are different studies in literature, for example, in resource-constrained project scheduling, where additional complex constraints are included. But for these real-life instances and the size of these real-life instances, we observe that we have long phases of local improvement until we reach a local optimum. And it seems that the structure is a little bit different than those of the benchmark instances. Therefore, we are currently designing thorough computational studies to evaluate and to find out what's the reason for these observations. And this is only the start. It was a lot of work to implement the data model, the basic algorithms, the machine representations, and we are now have a tool available which we want to extend in several different directions. The first goal is to improve the solution quality for benchmark instances so that we know we have the tool available which can yield very good solution. We are currently implementing parameter tuning framework to find best parameter sets for given problem instances. For very large practical problems, 20,000, 30,000, 50,000 operations, we want to implement a surrogate model to be able to solve those instances faster. And currently, if the environment changes, we restart the solver or the solution process with the current solution or the current state of the environment and the old solution. And we want to extend this so that we can react on environmental changes without restarting. And we want to incorporate information from external systems. For example, if a breakdown of a machine is predicted with high probability, we want to prefer another machine in the planning so that we are more robust in the execution of the plan. So, thank you very much. That's it from my side.
Thank you very much, Michael, for this interesting talk. Are there any questions? I see Victoria has her hand raised. Is that still from the last talk, or do you have a question for this presentation?
Actually, I think it is from the last talk, but I do have a question. So, but yeah. I only want to ask my question if there is nobody else who wants to ask a question.
Right now, I see no hands raised. So if you have a question, please use the raise your hand feature. If you cannot use this feature for some reason, please unmute your microphone and just say so. So please, Victoria, go ahead.
Okay, thank you. Thank you, Michael, for this interesting talk. I just wanted to ask you, you said that the real-world instances seem to be not the have the same hardness as benchmark instances have. And you said you're not absolutely sure why. Did you think here about the network complexity? Perhaps I I didn't hear it. I just wanted to ask, could this be a reason for the different hardness of
which
the
complexity?
So for scheduling problems, especially for the RCPSP, there are some measures defined which tell you how hard an instance is. And one of these measures is the complexity measure. There are several others. I don't know all of them by heart, but so we saw it for one in one of our projects that we had the case that the real world instances, the connections between all the nodes within one instance absolutely was not this comparable to the complexity of the network of the benchmark instance. So yeah, it was very interesting for me now to hear from
so yes, we are not quite sure, but this could be a reason. The connectivity structure of the operations, which is certainly true to a certain degree. But what I think is another important aspect is in real life instances, the operations and jobs already have a rough planning. A rough planning was already done with those operations or jobs, so they have dates, rough dates, where they should be scheduled, and additionally, there is a certain production structure, I think, which is repetitive in terms of the people or all the workflows have a certain structure, which I think are reflected in the data. So I think this is somehow they currently in production. They are currently planning, perhaps manually, and they do it in a certain way so that they can produce the products. And I think this influences the problem structure additionally. Rough planning, certain planning structure, and yeah, I think these are additional reasons. But I'm not absolutely sure.
Mm-hmm.
And just a quick question from my side, because we're a little bit over time. You mentioned you do rescheduling when something changes. Can you say something about how frequent those reschedules are and how long do you have time to do the rescheduling?
Those reschedulings are not that often. There's a periodic scheduling, or typically there's a periodic scheduling every day, and it depends if there are breakdowns. But at the very short time horizon, typically the plan does not change. There are additional orders in the future which are scheduled into the distant future, more distant future. We have special methods to do disruption management, which replans the short time horizon in case of major disturbances, breakdowns. For example, I didn't mention this, but there are special methods implemented.
And what is the running time? How long do you run until you have to present the solution?
Running times for benchmark instances is a few minutes, but if you have a few thousand operations, then there's a few hours.
Okay.
For really large instances. Therefore, we want surrogate models to have a faster system.
Okay, thank you very much, Michael, for this talk. Thank all the other speakers that have presented in this session. Before the break, I want to announce also that tomorrow afternoon at 16 o'clock, we have a special session again on dynamic optimization with talks from the industry. So Stefan Wagner is going to present the Josef Rössler Center on adaptive optimization in dynamic environments. And we have talks from Karl Schneeberger from the Industry Logistics Linz, and also from Gerhard Fehringer from the LISEC Austria, which is in the glass industry. So we have cases in the glass industry and in the steel industry, from practitioners presenting their viewpoints. I would be very happy if you can join us in these sessions tomorrow at 16 o'clock. So then it is time for me, I think, to conclude this session, and I wish you a very fruitful and a very, so to say, insightful further use of this conference. Thank you very much.
Thank you.